Hello, my name is Christophe Finot. In this presentation, I will discuss observations made in a fiber laser where we have tried to better understand the rich dynamics that can be experienced by dissipative breathing states. These results have been obtained through a collaboration between East China Normal University, the Aston University in United Kingdom, and the University of Burgundy in France. Ultrafast lasers are based on a fiber cavity. In this talk, we will consider laser operating at a telecommunication wavelength so that the gain is provided by an NearBiob fiber amplifier. The mode locking mechanism is based on nonlinear polarization rotations. This kind of lasers have stimulated hundreds of research works. However, there are still some limitations regarding the practical operation. Indeed, a stage of manual and empirical adjustments of the state of polarization remain usually required, which may partly prevent the simple turnkey operation. To overcome this issue, smart lasers based on evolutionary algorithms have been designed and implemented. It has enabled a fine-tuning of the parameters to reach usual modlock operation, where all the pulses are identical in the temporal and spectral domains from round trip to round trip. And the RF spectrum is made of narrow spectral lines equally spaced by the repetition rate of the cavity. Additional control has also enabled to generate pulse train at harmonic mode locking with repetition rates that can be twice or three times the frequency associated to the fiber cavity. Basically, smart lasers require a stage of measurement and also a stage of feedback where the parameters of the cavity are adjusted. Between the two, the adjustment is made thanks to an optimization algorithm, typically a genetic algorithm. The basis of the approach is to mimic the principle of Darwinism. An initial population made by a set of individuals, each individual having several genes that correspond to the parameters of the fiber lasers. The output laser property are then measured and used to evaluate a fitness function. This stage is very crucial as the fitness functions tell us whether or not the individuals are close to the expected goals. If the goals are reached, then the search ends. Otherwise, the best individuals in the population are selected. They are becoming parents of a new population so that crossover between the genes happens, and mutation can also affect the genes. This leads to a new population that is applied as a feedback on the cavity, and the algorithm goes on. Our goal in this contribution was not to target a usual mode locking state where the pulses are identical from one trip to the other. We have focused our attention to the generation of a new or more complex state. We are indeed looking for breathing state where the pulse evolves periodically both in the temporal and spectral domain, experiencing cycles of growth and decay with large spectral expansion and compression stages. Such pulse can exist as single pulse, as doublets, or as more advanced molecular complexes, as we have demonstrated in previous studies. So we have implemented a smart cavity that can deal with such unusual structures. As measurement, we have recorded the direct temporal intensity profile as well as measurement of the shot-to-shot optical spectra, which is possible thanks to the dispersive Fourier transform technique. These shot-to-shot measurements are crucial to catch the breathing behavior of the pulse, as the average behavior is not relevant in our case. One precious quantity we have considered is the radiofrequency spectrum, where the breathing behavior manifests itself as new breathing frequencies that differ from the main line typical of the cavity repetition rate. Additional measurements involve the direct record of the RF spectrum, as well as the use of a simometer to test the stability of the frequency under investigation. The genetic is then used to control the state of polarization within the cavity thanks to three electrically adjustable wave plates. Here are some results we reported last year, stressing the convergence of the algorithm that works after only a few generations. We obtained the expected briefing states with new sidebands in the RF spectrum. Note here that the period of the briefers in terms of round trip is quite long, leading to sidebands that are very close from the main frequency. Since then, we have focused our attention on states exhibiting some much lower briefing periods. Here is an example of such breather where the temporal and spectral periods of the briefing are close to 5 times the round-trip duration of the cavity. If we now change very slightly the power, we observe that the pattern becomes fully periodic. The difference between the two states can be better seen on the RF spectra. In both cases, a peak is located at the frequency repetition divided by 5. But whereas this peak is quite broad at 33 milliwatts, it becomes very narrow at 74 milliwatts. We can therefore make a clear difference between a frequency unlocked state, as observed for a pump at 33 milliwatts, and a frequency locked state observed at 34 milliwatts. We can also observe those differences in terms of spectral width of the RF spectrum, as well as the long-term stability of the two regimes. Here we see that in the frequency lock state, variation can be of the order of a few hertz only. What is particularly remarkable here, this is that this frequency locking process does not imply any external driving frequency. It really links the repetition rate of the cavity to the internal frequency of the briefing state, which is controlled by the pump power. And when we slightly tune this pump power, we observe that the RF spectrum may really differ. Quite significantly, the spectral lines of the log state are all equally spaced by the repetition rate of the cavity divided by m. Note that rather dense comb can be achieved. Here, a decrease by a factor of 41 of the frequency is achieved, so this really opens up new possibilities. What we can also make out is that the most powerful spectral line is not always the first spectral line. Here this is the second, here this is the ninth. So it can be the nth one. And those two parameters, the m and n parameters, lead us to define the Wiging number, which is the ratio of n over m. In this map, we show the radio frequency spectrum according to the PEM power. And we clearly see that we have frequency locked and frequency unlocked states. And we can also notice that the frequency of the main radio frequency line continuously increases with power. For each frequency lock state, we can attribute a Wiging number. And what is particularly intriguing, this is that the Wiging number are not random at all. The Wiging number shows a hierarchy of a Faraday tree. A Faraday tree is built by adding the numerator and the denominator of two parents, and it gives the children. So we use this formula, and with such a formula, we can build this kind of tree. So more explicitly, in our case, this is the evolution of the main peak of the RF spectrum according to the power. The longest state has a Winding number of 1/5. Then a shorter state is quantified here by the Winding number of 2/9, which is the result of combining 1/5 or 1/4. We then see a Winding number of 3/14, which is the result of the combination of 2/9 and 1/5. And then we have two shorter states with the same length that have Winding number of 5/23 and 4/19, and they can also be predicted by the Faraday tree. So now I think that you have understood how it works and how remarkable it can be that we can build this hierarchy of numbers. But there is another remarkable property of the frequency log system. This is that the length of the various steps is not random. The dimension of the gap between the various stairs is found to be fractal, which is a phenomenon usually known as the Devil's staircase. In an ideal Devil's staircase, a fractal dimension of 0.87 exists. In our case, we have found that the fractal dimension is 0.9. And experimentally, what we have done next, this is to change the polarization state and to see if our conclusion can be reproduced. And we obtain the same kind of behavior with other Faraday trees that are followed. In each case, we also observed the fractal numbers that are in agreement with the Devil's staircase. Finally, to confirm all those experimental findings, we model our experiment by using numerical simulation based on the nonlinear Schrödinger equation for each lump element of the cavity. This numerical simulation enables us to retrieve all the previously discussed features. And it also confirms that changing the intracavity loss by changing the polarization states can enable us to reach other Faraday trees. So to conclude, we have emphasis in this talk frequency locking operation of a laser that works in a briefing state. This enables us to achieve high stability, high signal-to-noise ratio, and a very narrow line width of the spectral lines of the RF spectrums. Once frequency locked, the laser is robust against small variations of its parameters. In order to find easily the states, we have implemented evolutionary algorithm with a carefully designed merit function. Here, this is a quite crucial point. The behavior against power of the frequency modlock laser remarkably shows the hierarchy of a Faraday tree and the fractal characteristic of a Devil's staircase. Finally, all our experimental observations have been confirmed by numerical simulations.